Right, now we're coming to the last session. Possibly one more, I'm not sure, but let's see how we go. What we're going to be doing, it's quantitative chemistry again. I almost said quantitative easing, but quantitative chemistry. What we're looking at is we're going to look at concentration first. Now, you remember everything we're doing here in chemistry is we're looking for the mole. The mole allows us to go through, I know it sounds silly, but I call it the mole hole. It allows us to go backwards and forwards through the little tunnel, right? Only at the mole level can we do this, okay? There is one exception which we'll deal with shortly. It's on gases that are at the same volume and same temperature. But first of all, we've got to look and we've got to find the number of moles, okay? There was a download which is there, which is free, which has got the little mole in it. I'm just going to summarize that at the end. But first of all, concentrations, okay? What is a concentration? We all know that we dissolve something in something or we dilute something. So essentially, we are going to be either dissolving or diluting. That's what this is about. Now, concentration is given the number C, all right? And C is measured in moles per cubic decimeter, and please remember 1 cubic decimeter is 1 liter. 1 cubic decimeter is 1 liter. So whenever, once again, you can see the mole is the common thing here, because that's what allows us to go backwards and forwards through the tunnel, isn't it? That's the key to these stoichiometry calculations. It's the key to the whole lot. Right. So what do? We say, right, first of all, whenever we get a calculation involving concentrations, they will tell us either, okay, a volume, okay, the volume is N over V, moles per cubic decimeter. Moles is N, V is the volume. So we're going to be given a volume, a mole, number of moles, or a concentration. The volume generally might be given in centimeters cubed. It could be given in milliliters. It could be given in a various number of forms, liters. The first thing we do is we convert to decimeters cubed. That's step one always. Unless it's given in decimeters cubed, we convert to decimeters cubed. Please go to that Kilimanjaro table and have a look how to do that. It's terrible to go through all of these calculations and find that in actual fact, a silly mistake was converting the decimeters cubed, okay? The next side is number of moles. The third is, all right, moles per cubic decimeter. Okay, moles per cubic decimeter. So what have we got? Hello, we've got three unknowns, three that we need there, three different items, right? If we're given any two out of the three, then we go and calculate the remaining outstanding one. So for example, if we're given number of moles and a volume, we can calculate number of moles and a volume, calculate concentration. If we're given concentration of 0.5 moles per cubic decimeter, all right, then we know that we've got 0.5 of a mole in every cubic decimeter, right? So therefore, we would be able to either calculate volume or number of moles, depending upon which other one we're given. So always look which two are given out of the three and calculate the other one, because you're going to need it, all right? So concentrations generally, what do? We straight away, we look for which of the two have we got and calculate the third. Usually they will say it's 0.4 cubic and we are given, let's say 200, and we've given 250 milliliters of solution. Okay, milliliters we've got to convert to decimeters cubed, okay? So now, if we're going up, remember, we've got milliliters, okay, centiliters, deciliters there, and liters, right? Milliliters, we're going up, therefore we must divide, right? And we're going up to liters. Remember, this is where you're going to convert to cubic decimeters, isn't it? That level. So we've got to first of all get it to liters. So we're going to divide by 1, 2, 3 steps, which is 1,000, its volume. So that is going to be 0.25 liters, which is the same thing as 0.25 decimeters cubed. Therefore, we now have volume. 0.25 cubic decimeters. Well, we've got volume and we've got C. So C is equal to N over V. Let's rearrange. N is equal to CV, which is 0.5 times 0.25, which is going to be equal to, let's just have a look, 0.5 times 0.25, come here you, mode 1, 0.5 times 0.25 is equal to 0.125. What? Moles, correct? 0.125 moles. That is exactly the approach we take with all of them. Look what you're given out of the 3 and calculate the other one. Invariably, you're given a concentration and a volume. Okay? But write down the 2 that you've got and calc the other one. The error source here is fundamentally not knowing how to calculate it into decimeters cubed. If it's in milliliters, centiliters, or whatever, you go up always until you get to the liters. If it's in centimeters cubed, say, cc, cubic centimeters, okay? This is millimeters cubed, cubic centimeters, decimeters. There we're only going to go up 1 step because we're going to already get to decimeters cubed. And we're dividing by 1,000, right? So very important to know those conversions. Okay. Now, let's have a look at another concept, okay? And in this case here, okay, well, let's just do an example. Okay, I've got an example here. Calculate the concentration if we dissolve. So, what are we going to do? We're going to dissolve 75 grams of Cu copper sulfate in 250 milliliters of water. What is they asking us the concentration? N over V. First thing, milliliters, we need to convert it to cubic decimeters. So we say milliliters, centiliters, deciliters, liters. We're going up 1, 2, 3. We go up, which means we make smaller. Therefore, we divide, and we're dividing by 10, 100, 1,000 is equal to 0.25 liters, which then liters goes across to cubic decimeters, which is 0.25 decimeters cubed. Volume, done. Volume is equal to 0.25 decimeters cubed. Okay. Next we say, okay, we need N, number of moles. How do we get to number of moles? Number of moles, quite straightforward. We do the following. We say, okay, we've got we need concentration. Well, we've given a mass and a compound. So we need to go to, let's see, what are we given here? We are given 75 grams of copper sulfate. Therefore, N, number of moles, is mass given over mm. Remember the one above, we have to work out mm. And the molar mass of copper sulfate is 63.5 is the copper, plus the sulfur is 32, plus 4 times 16, okay, which gives us 159.5 grams per mole. Okay, now, therefore, what have we got? Now we're going to work out number of moles. Remember, always get to moles. We're going to say 75 over 159,5, and that's going to give us 0.4695. Therefore, concentration is number of moles, there we go, 0.4695 divided by the molar mass, 159.5, and the final answer is going to be, my bad, it's 0.46 divided by the volume, which is 0.25. Okay, the answer is 1.878. And that is moles per cubic decimeter. All right? So therefore, in every liter, we're going to have 1.878 moles. Okay. Right. Now, the next one is one that appears, and it says, let us take, for example, this. Let me just get it up a little more. Let's say we have the synthesis, which means manufacture of, ammonia again. Okay, like so. And let's balance it. 2, 3, and 1. Now, therefore, we take out and we say the ratio or the recipe is one of those, 3 of those, moles in this case, gives us 2 moles of that one, right? Now we say this, we say, right, if it's the gas, if they tell us that the gases are all at the same temperature and pressure, okay? If they are all at the same temperature and pressure, then what you can do is you can equate the volumes straight away instead of the moles. It's the same thing, only at the same temperature and pressure. If you go and you work it out using the table, where you take number of moles, divide, do this, do this, do this, you get the same answer, okay? Because what you've got here is, this then means that one of those volumes plus 3 of those volumes gives us 2 of those volumes, okay? The last part, okay, of this is the molar gas constant. Molar gas constant, all right? And it is this: 1 mole of any gas at STP, standard temperature and pressure, all right? The temperature is equal to 0 degrees Celsius, 273 degrees Kelvin, and the standard pressure is equal to 101.325 Pascal, or 101.325 kilopascals, all right? Those you've seen before, we're going to deal with them again when we get to physics, but that's the standard temperature, standard pressure. 1 mole of any gas at STP occupies the same volume, 22.4 cubic decimeters. Okay? Therefore, the moment, now here's the thing with this, okay? The moment you see, when you're reading it, they talk about standard temperature pressure, STP, immediately you should be triggered to think of 22.4, right? So what would we say? We'd say, right, let's say we have, I don't know, let's say we have 10, let me just make this a little clearer. We have 10 decimeters cubed of ammonia, let's say of NH3 at STP. Okay? Calculate the number of moles of the gas. Straight away, the trigger says, whoa, hang on, I remember STP. Straight away, I go to 1 mole equals 22.4 decimeters cubed. Then I put down, what have I got? I've got 10 decimeters cubed, therefore X moles. What do we do to calculate these? We cross multiply, right? So therefore we've got 10 times 1 is equal to X times 22.4. Therefore, x is going to be 10 over 22.4. So x is going to be, let me just put on my glasses, 10 divided by 22.4 is equal to 0.4464 moles of NH3. Okay, then therefore, how much mass of NH3? Let's say they've asked us, okay, how much mass of NH3 gas is that? Well, we know straight away, we say, right, number of moles is equal to mass given over molar mass, right? Molar mass of NH3. Can you see? It's just the same repeated steps. We always work out molar mass, we always work out moles. The moment you see mass, go to molar mass and work out n number of moles. The molar mass of that is nitrogen's 14 plus 3 times 1, which is 17 grams per mole. Let's put it in. So therefore we say number of moles is 0.4464 is equal to mass over 17. Therefore, the mass is equal to 17 times 0.4464. And the answer is times 17 equals times 0.4464 is equal to SD 7.59. Right? 7.59 grams. Okay? So there essentially we have, okay, we have a fundamental part. We've got the volume, let's say we've got the concentrations, okay? We've got masses, we've got molar masses. So what was I saying? I was saying that everything is find the moles. Find N, find the number of moles in all of this lot, okay? Then I did that little download because I was just wanting to illustrate it. Number of moles, right? And I did it like this, all right? First of all, the way to get moles is if we are given a mass. Given, we say number of moles is mass given over molar mass, right? That's the first way of working out moles, okay? The second way is if we've got concentration. Concentration, right? Concentration is N over V, number of moles over the volume. Therefore, number of moles is concentration times volume. And hey presto, they give us volume. Concentration, okay, is the number of moles over the volume. The third way that we said of finding these things out was going to be gas at STP. What's the trigger? STP is the trigger. 1 mole equals 22.4 decimeters cubed or liters. Okay, just to confuse you, they might give you liters. 1 liter is 1 cubic decimeter. So what do? You convert and you put X is equal to, and you put the given decimeters cubed there of the gas, right? And the fourth way of doing it is a formula called PV equals nRT, which we will deal with at a later date, okay? So there we have, in essence, the last remaining calcs, okay? I'm going to do one more session after this, which is the short one, where I'm going to do a full stoichiometric calculations using some chemical equations, and we're going to go through it step by step. In the download section, there is the standard table with all the descriptors on it that I'm going to go through and show you how to use the table, right? It's glaring. Well, first of all, if you follow the method of the table, doesn't matter which calc you're doing, acids and bases, you can even use it in electrolysis. If we're doing equilibrium chemistry in grade 12, it doesn't matter. The rules and the processes stay the same because essentially it's all about finding that mole. so that once we've got the mole, we can go through the mole hole, the tunnel, backwards and forwards, because we preserve the ratios as we go through it. Okay. Thanks for watching. That's session 22. We're going to move on and we're going to look at session 23, where, as I say, we're going to do some stoichiometric calculations. Thanks. I'll see you on that one, then we can finish it. And hopefully then you'll look at the questions and some exam preparations and things like that will also be available shortly. Thank you.